Good day and welcome to Math in the PM. I'm Joel Sindel. We're looking at 7.3 similar polygons today. Okay, your attention's up here, Big E. W-E. Not using full names on the recorder. Okay, anyways, so pay attention up here. So polygons, multiple sides. That's poly. Okay. Later on, we're actually going to look specifically at triangles too. Now, which polygon is a reduction of another? What is that scale factor? So we have to have the same what we call proportions too. A, B, and C. One of them doesn't fit. Which one of those is not like the other? Of course, they're all different sizes. You got that. So somebody else too. Somebody from the middle here. Which one, A, B, or C, does not quite seem to be in the same proportions visually? You can tell this without measuring. C. Why do you say C? You're correct. Yeah, the bottom L part needs to be a little longer, and I'm going to just draw on the board. You can just visually see that if this was what you have, it would work, right? Okay. So I think you intuitively know what scale enlargements and so on look like, right? Reductions. Okay. So which one's a reduction of the other? Let's answer that question on paper here. B is a reduction of A. C, I'm drawing here, is neither. What is the scale factor of the reduction? If it's truly a reduction, it doesn't matter which one you take to compare, but I'll choose. There's bottoms. 4 turns into 2. You remember? We use the letter K. And B, positive. Okay, the announcement's over. And I was saying, K factors. You guys remember this. What goes on the top? What goes on the bottom? Which one has the scale? Which one has the original? Top or bottom for what and what? Scale on top, original on the bottom. So since we're saying that B is a reduction of A, we're going to say B is the scale measurement. So 2 bricks across, 2 spaces across, compared to 4. That's a 1 to 2 or a half. That's the 5 scale factor, right? Does that make sense? Afterwards, we've been doing this for a couple of sections. Should know. What if you looked at it the other way around? You describe polygon A in relation to B. That's basically thinking of B as the original. Well, A is and how is A? If you think of B as the starting shape, an enlargement. And I can already see this. 2 turns into 4, so it's times 2. I'll put it in green though, just so it stands out again. K factor in this case is 2 to 1. Does that kind of make sense? Maybe new to you. Then we've already talked about C. Why is C not an enlargement of B? Because the bottom is too short. Right? I drew it out here, but it would have to be longer. Long enough. I'm going to use a math word, in proportion. Side height. In proportion means like there's a ratio 2 to 1. Okay. 2 times the thing, stuff like that. Okay. We cool with this? This lesson and the following one, we'll be studying the properties of polygons that are either enlargements or reductions of each other. And we'll use those things to solve problems. So some terms to review. Did you guys do this back in grade 7, grade 8? Name shapes by their vertices, the letters at their vertices. Vertices are the corners. Okay. When we name these, there's a particular way we should try to do this. A, B, okay, this one, since we went in this order, it didn't matter which order it went. I actually used to go clock. What I cut and paste on. A to B to C to D. Now, if I'm doing that, and I'm saying this, do you guys ever see this wavy top equal sign before? Have you seen it? Grade 8? Not? What does it mean? Ah, if it's a double wave, that's sort of equal to, approximately equal to. This isn't the same. This is called congruent. It's an equal sign with a wave on top. And congruent doesn't mean equal to, but it means it's proportional to. And proportional is that math word. It's in a ratio. So it could be 2 times as big or 3 times smaller, 1/3 the size. But as long as all the angles are the same and the sides are in a ratio that is constant throughout the shape, then that's congruent. And that's what this means. And I'm going to terminology for review. I'll write this one down right here. You will too. Right? So that wavy equal sign with the wave over. You're writing this down right now. It's congruent. Congruent means that the shape is proportional. We've been doing congruent shapes, enlargements and reductions are congruent to each other. The angles remain the same. The sides are a multiple. Here's what I wanted to point out when I started. You notice how corner E is in the same kind of spot that A is, right? So if I'm naming these shapes, I want A and E to be start. You notice how corners B and F are at the same? I'm going in the same order with all these letters when I list 2 congruent shapes. That's important. And then corresponding sides, corresponding angles. So I'm going to switch now to ink that doesn't disappear. We're going to say that the corresponding sides or the congruent sides, AB. You guys ever use this kind of terminal or symbol for a line segment, right? Back in the day, grade 7. Corresponds to what's like side AB on the larger shape? Yeah, it's at that angle that's on the left side. There's 3 other line segments. Can you guys get those corresponding sides named like that? Okay. Go ahead. And then we'll talk about the angles. Go ahead. I'll pause the video while you do it. Yeah, I'm resuming recording. There we go. Are we good with that? No. Corresponding angles are actually equal. even though the shape's larger and smaller, the angles remain the same size. And I'm going to show you something. So angle A, angle E, they're the same. There's two ways to do these, and I'm going to do only for A and E, the long way, and then tell you why we can do it the short way. Corresponding angles. Angle BAC is the same as angle FEH. Now that's the long way to do this. Did I do that wrong? I totally did. AD, bad Shabelka. I wasn't looking at the diagram when I did that. FEH is correct. They're the same angle, but we name it that way because you always put the angle, the vertex in the center, right? However, it would not be ambiguous in this diagram. When I say ambiguous, you wouldn't be wondering what is he meaning by this. If I just said angle A and angle E, in this particular diagram and shape, you can do that. And I think you should if it's short. So, when can I use the shortcut when it's not ambiguous? But I'll show you where you can. Look at this. If I just say angle A, do you know which one I'm talking about? If I say angle A, I'm not sure if I meant that part of angle A or this part of angle A. Does that make sense? So I can't say angle A in this diagram. I would have to say, if I want the green one, I'd have angle D. Why did I say D in my diagram? I'm going to erase this, don't worry about this. BAC or angle A could mean angle CAB. Do you see why you'd have to use three letters to indicate which is which there? Whereas on the shapes there, there's no other alternative other than the reflex angle. I'm not going to try them. Okay, continuing on, then I think this one's pretty simple. Angle B is the same as angle F. I'll switch your order up here. Angle G and S, C, F. Then angle D. Okay. Okay. Reading this, when one polygon is an enlargement or a reduction of another polygon, we say they're similar, or congruent is the word I was using. Similar polygons have the same shape, but not necessarily the same size. Here's two similar pentagons. You notice how all the angles are the same. But you can't just have all the angles the same. You also have to have their sides corresponding, or multiples of each other. Yeah, the sides are corresponding. Okay. Now let's just take a look at these diagrams here. It's very technical, so if you just see the chart all at once, it's like, wow, I can't make sense of it. So here we go. I'm going to find PQ on the small diagram. That's this. So PQ is just like PQ, but you notice we have this one with P tick mark. Q, oh, I can't make a circle there. A Q with a tick mark there. All of those letters have a tick mark just to say it's the second shape. Okay? And that's 3 in this case. So 2 here, 3 here. So when you compare them as a fraction, it's 3 out of 2, or 1.5. Angle P, okay. And you can do that all throughout with all these other shapes. QR, 1.5 centimeters, 2.25 centimeters, and so on. They're always 1.5 times bigger on the other shape every time. Then you know, if one of those shapes came out to, or one of those sides, say this one here came out to a different ratio, then this would not be congruent. Okay? Corresponding angles are always the same. say this pentagon, PQRST, and P tick mark, the tick mark pentagon are similar. This is missing. You add this in here, the font, equal sign with a wave on top. Okay, that's the similar or congruent symbol. You have to add that into your notes. We're missing right there, right? Okay. We did all the math, or the chart does all the math. We have a scale factor of 3 out of 2, or 1.5. You think the other way around. As a reduction, the reduction's on the left, and it has a scale factor of 2/3. Pick one way or the other, unless it's often explicitly stated which one you're starting with and which one's the scale. Draw. The two polygons are similar, angles are equal, corresponding sides are proportional. You multiply by the same number, get every other measurement scaled up or down. It's also true that if two polygons have these properties, say the other way around, then you know they're similar. So you can say vice versa. And that's not always true. It is. More of what we've done before. I'm going to talk to you right now and give this first example a go. When you see this, it's just like when I put x into the equation, AB. What's the phrase that pays? How do you solve this just with the calculator? What do you multiply? What do you divide by? What do I say? Let's multiply, and that's the diagonals. Then divide by the lone. 8 times 3 are the diagonals. 8 times 3 divide by 2. It only works if there's no addition or subtraction. AB is equal to, use a calculator. 8 times 3, though, is 24. Divide by 2 is 12. That's it. Now, I'm going to skip something and just tell you what you need to do next. You need to do 2. You need to check mathematically that these are proportional. The best way to do it is to say, I think that side AB compared to, maybe this is. Okay, I'll start this one off. So is AB to HG. What's the ratio there? Well, that's 8.5 to 8.4. And I put it in the calculator. I'll do it right now. It's a division code. 8.5 divided by 8.4. I'm going to keep 3 decimal places behind me. 8.012. Now, if this is proportional, this side to this side, then these sides should come out to be the same decimal number, 2.5 and 2.4. Let's just see. So A or BC compared to FG, 2.5 to 2.4. And you are expected to actually do it here. And it ain't. It's 1.04. So the top and bottom shape are not. I'm going to call it this one the top shape. Bottom. I'm going to call this the right. For obvious reasons. Okay. So far, I've only proved that the top and the bottom aren't proportional. You're going to have to do some comparisons to the right and the top, or the right and the bottom. Same way, though. You take comparisons by doing their ratios of their sides. And if it comes out to be the same every time, then they're proportional. Now, any questions on this type of question? I've gotten you started. Lastly, you're going to finish this, right? These polygons are similar. Oh, I wanted to point something out. One thing. Now, similar shapes, or there's a previous thing. Both things have to be true with similar shapes. Their angles are equal, and their sides have to be proportional. Now, looking at what we were just doing, I think you'd agree that these angles are the same, but the sides aren't proportional, are they? So angles can be equal. That doesn't guarantee that the sides are proportional. They're not similar. So you're going to finish that problem. Back to this. We're told these are similar. Determine the values of x and y. I didn't even make that a problem because you can just draw it out. So look at this. If this is 147, what is angle x? Tell me. You got it on the paper. But we're told it's similar, so what does that mean about their angles? They look like it too, right? What are they? The same. There's no arithmetic to do. We're going to just say that x is equal to 147. And then y is equal to, well, y looks to be in the same spot as the other corner, 64, right? Okay, now we'll do A, calculate the length of side A and side B, etc. So, you got to set up a fraction system. I'm going to do it this way. You could do it, you could set them up two different ways. I'm going to say the side that's, this will be my big shape here on the middle. I'm actually writing that down so I keep my thoughts ordered. Actually, maybe I'll move those words underneath the actual fraction system. Now, here's what it's important. You notice that 12 and 4.8 are basically, they're similar sides, right? Here's what I'm doing. I'm going to say 12 on the big is like 4.8 on the little. Does that make sense? Just like 5 on the big is like A on the little. Does that make sense? How I set that up? The left side is information from the big shape. The right side is information from the small shape. Cross multiply, divide by the lower. You guys know how to do that, right? And then you can do the side B, same kind of method, big little. I'm going to leave that to you. It won't take you long. You'll be able to be done. And that's it for today. Monday we'll work on the rest.